Colin, thank you so much for joining us once again. And the workshop last week on power and power considerations was very, very interesting. And what I did is I did upload the edited video for everybody who couldn't join us to be able to go through it. And also, of course, for those who were there who want to have a look at those equations again and those examples again. So this evening, you're going to be covering connectivity and communication with us. And thank you very much. Connectivity and communication is absolutely essential when we have any asset collecting data anywhere, whether it's in orbit, whether it's remote, in a wilderness area, in a field. So all of the concepts that you're going to share with us are really, really important, not only for satellite design, but also for smart farming, smart agriculture, and IoT applications in general. So with that, Colin, if I may hand over to you.
Excellent. Thank you very much for that intro, Judy. I think, yeah, just to sort of mention to everybody, last week we delivered the power course, and you'd find very similar sort of outline that we are going to cover today. So we'll cover a little bit about some of the history. We'll cover definitely the one element is most kids come out of school saying, why did I need to study mathematics? And why was it useful? So it's always an element I'd like to include in all of these courses. So we'll cover just a little bit of mathematics and how that relates to connectivity and communications. We'll cover some aspects as well around the Mars project that you have on the go, and we'll cover a little bit about the assignment. But yeah, it's really an action-packed presentation. I'm going to try and do my best to cram it within the 1 hour, but also sort of try and keep it interesting to yourself. As I sort of mentioned last week as well, you know, I don't like to call this a presentation. I'd like to call it a conversation. So at any point, you know, if you could break out of your usual style in classroom and that type of thing, and have a conversation with me, you know, so you don't need to raise hands. You could just go ahead, unmute, you know, start speaking, make a comment, ask a question. I'll ask a few questions during the presentation itself. But you know, I'll sort of wait for probably around about 2 seconds and then move on, just purely based on the amount of time that we do have limited this evening. In sort of keeping in tradition with some of the other courses, I always like picking a story. You know, this time I'm not going to talk about Michelangelo's painting on the Sistine Chapel, as you can see here. But very, very quickly, the one story, you know, I'd like you to think about is it was probably fairly later on, you know, in my childhood that I realized, you know, when I bought a packet of chips or French fries, as some of you may know it, or when I've actually ate some mash, or when I bought myself some Simba chips or crisps, as some of you might call it, you know, in the store, or during breakfast had a hash brown. You know, these are all fundamentally quite different things, and I didn't realize that they're all the same thing. They're essentially all, of course, one of the questions I'd like to ask you now. I'll give you 2 seconds if you can tell me what is the commonality amongst all of those. You're welcome to just shout it out. Any ideas? Yeah, so it's essentially all potatoes. You know, so some of you may be discovering that yourself today, but they're all the same thing. They're all potatoes. Yeah, I guess as I sort of grew into adulthood, I've also gone into learning how to make these different variants, which again, I mean, they fundamentally taste completely different. Absolutely yummy, but yeah, what has that got to do with what we're talking about today? So later on, you're going to start to see when we get to specifically the electromagnetic spectrum, and we talk about frequencies across the entire spectrum. So we'll talk about things like radio frequencies, we'll talk about light, microwaves, X-rays, gamma rays, etc. Essentially, they're all the same thing. And no, they're not potatoes, but it's essentially light. The one commonality that you look at anywhere on the electromagnetic spectrum is that they all travel at the same speed, which is the speed of light. But more about that coming up. What we are going to cover in the session would be things like starting straight with the EM spectrum. We'll talk a little bit about waves. We'll talk a little bit about radio waves, cover the internet. You'll find that all of our courses are aligned with the UN SDGs. In this particular instance, aspects of the SDG 7, which covers things like renewable energy and renewable resources. You'd find what is the alignment with the UN SDG 7. As with all the other courses as well, we'll mention something around satellites, Mars, and we'll close up with the questions and assignment. You'll find I'll just flash up the questions and assignment, but we won't necessarily go through that on today's talk. That's more for you to complete on Canva as the platform itself. Quite a lot of stuff to get through. I have to say that this, for me, is one of my favorite things to talk about, and we could literally spend a complete day on that. But yeah, perhaps we could continue the conversation on Canva itself. So you're welcome to interact with us on Canva, ask any additional questions there. By the way, if you feel more comfortable popping through questions and comments on the chat, please by all means go ahead and do that. If you don't feel that you want to talk specifically, so we do have, I know Judy's online, we may have Grace that might be online, so they will certainly assist in terms of answering those questions or raising any particular comments. Great. Now, the one thing that I ask is, in this particular picture, you'll see that there's a droplet. A lot of you have actually seen this, whether it is tossing a pebble into a river or adding in a sugar cube into your coffee or tea, and you'll start to find that waves are being propagated. So essentially what we see happening here is a disturbance in the water, and that initial disturbance could be caused by anything. It could be by you dropping something in, it could be by rainfall, but once you start to disturb the surface, it starts to create a wave, okay, that then a transversal wave that starts to move through water, etc. If we had time, I'd love to have a conversation around the ocean and more specifically about waves. But I'll leave you with a question, which maybe you can go and research on your own, right? Why do we have waves, and why do we have these big crashing waves that arrive onto the shore? So remember that as budding scientists, I'd love for you to constantly question everything around you. Always be curious about the world that you're in. Constantly ask yourself questions and make sure that you can explain it to other people. And the way that you can explain it is in the language of science. Okay, so that is just some homework for you. You're welcome to share some of your thoughts on the Canva platform. Yeah, this is essentially something that you can actually continue, so I'll just skip straight past that. So there are different types of waves, but more specifically, although you see there are three types of waves here, but generally you can think of just two basic ones, one being a mechanical wave and the other being electromagnetic wave. Mechanical waves are waves that, again, that are caused by some sort of disturbance. That disturbance could be the way mechanics sort of affect it and in a particular direction, right? So you'll find that mechanical waves are split into two. You have a longitudinal wave and a transversal wave. And examples of that would be sound wave for longitudinal, and the transversal would be a water wave. I think I do have a slide coming up that gives you a graphical sort of representation of how these two sort of are differentiated from each other. But on the electromagnetic wave side, they are really quite, it's essentially one type of wave, but it's classified in, various different things that you already know about. You know about microwaves, you've heard about radio waves, you've heard about infrared, ultraviolet, etc. So hopefully by the end of this talk, you'd be able to go and explain to your friends and family what each of these different elements mean, and you could probably share some examples around that. So just a reminder, I'm going to sort of push through all the various different slides coming up. Just feel free to either speak, share your comments, questions, or just go ahead and pop it into the chat. So the the longitudinal waves are also called compression waves, and you'll find that typically the motion of the disturbance is in line with the waves itself, right? So something to think about here would be a slinky, right? So if you push a slinky along its axis, you'd start to find that it moves along in sort of a wave. Another way to think about longitudinal waves that happens to all of us. How many times have you been driving down the highway and you suddenly find that you're driving at a speed, and then all of a sudden you slow down almost to a stop? And then after some time, you then start to pick up speed again. But looking around, there's clearly nothing that has happened. There's no accident. There is no obstruction on the road. But you start to find that cars speed up, slow down, and then speed up again. Okay. This is an example of a longitudinal wave. So if you looked at traffic from the top, so there might have been an accident that happened earlier, or some sort of reason or obstruction on the road that appeared that caused one car to slow down. And what actually happened is that there's an effect. As the other cars came in behind it, those cars then started to slow down. And then, of course, with a number of other factors. So if you think about braking time, if you think about acceleration time, if you think about response time to actually hitting the accelerator pedal, all of these come into play that actually creates a longitudinal wave that happens in traffic. So the next time, think about how you would like to explain traffic to your parents, while sort of driving along the highway. Another type of wave, as we said, from a mechanical standpoint, would be a transversal wave. So if you take a piece of rope, you tie the one end onto a fixed point, say on the wall, you hold the other end and you start to move it up and down, you'll start to see these waves appear and move from one end from your arm side and basically slam against the wall. And in some instances, you'll also find that the wave reverses and comes back from the wall towards your hand. So that's essentially the wave traveling along. And remember that with waves, you'll also see later on that they can be reflected from surfaces as well. So really cool concepts to familiarize yourself with. I'm just trying to understand. Okay, so before we get to the electromagnetic spectrum, it's key to understand things, the electromagnetic effect itself. So a lot of you may have played around with magnets. I love playing with magnets, and you'll find them in speakers, in microphones, you potentially in microphones as well. You'll find them in motors, so a lot of you, if you are into sort of breaking things apart, you should be able to find magnets in a whole range of appliances and devices. And they have some interesting properties, like you can see up here. The one aspect is that we all know that if you take a north pole of a magnet and the south pole of a magnet, you'll start to see them attract. Now, in that first picture that you see up on the left-hand side at the top, you'll see that there are lines or magnetic fields. Now, you can't visibly see those magnetic fields, but if you want to expose them, one way to do this, and I think a lot of you might be familiar with this easy sort of project, is if you get a piece of paper and you get a bit of iron dust or iron shavings, and you sort of sprinkle it up on the top, and you place your magnets at the bottom of the page, you'll then start to see these magnetic field sort of start to expose itself. And you can play around with the magnets at the bottom. So if you then go to just a single bar magnet, as you can see in the middle, you'll notice that that particular field formation would form. When you take two opposing sides of the magnet, so whether it's two north sides of the magnet or two south sides of the magnet, you will then start to feel that they repel each other. Um, I particularly like playing around with these neodymium sort of little magnets, very, very tiny and very, very strong. It's almost impossible, when I sort of play around with them to sort of bring them together if you've got the opposing fields together. But if you swing them around and they attract and they stick to each other, it's very, very difficult it requires a bit of force to pull the two sides apart. So if you ever come across those little neodymium sort of magnets, very, very cool to play around with them. The other aspects about the EM effect, we know that within the Earth itself, we have an iron core. And because we have an iron core in the middle of the Earth, it has now created this huge magnetic field. And essentially, the picture in the middle shows you exactly what a magnetic north and a magnetic south essentially looks like. But yeah, if you ever ask the question, if you pull out a compass and you sort of spin that around and tries to find north or south, you can explain, hopefully you can explain exactly why that actually happens. But again, that's another point of discussion if you'd like to sort of share your thoughts on the Canva platform. The last element that I want to cover from a magnetic field perspective is that we can create a magnetic field using the electromagnetic effect. One way to do that is essentially if you take a piece of wire, you apply current through it, you'll then start to find that a magnetic field forms around it. And the one way that you can convince yourself of this is utilize the same experiment using a normal magnet, right? Get a piece of paper, throw some iron shavings on the top, run a piece of cable at the bottom, and pass a current through it, and you'll start to see a magnetic field form. Now, an interesting thing happens when you take a piece of this cable and you wrap it around in a coil, right? And it starts to then produce a magnetic field that looks like a bar magnet, right? So compare the picture of the bar magnet at the top middle to the bottom, the middle left-hand side picture, and you'll see that it starts to look fairly similar just in terms of what that magnetic field looks like. So tons and tons of cool things that you could do with magnets, but yeah, I mean it's such an awesome type of force that exists. There's something that we don't really see, but basically that definitely exists. So just hopping on to this next one. So the electromagnetic spectrum. So essentially, story are told at the very outset, sort of lends itself quite nicely to this. We've heard of different types of elements like X-rays. We've heard of infrared. We've heard of light. You've heard of radio waves, et cetera, et cetera. But essentially, it is the one thing. The one commonality that you have is it's really a different flavor of light, right? It's different frequencies. Remember, it's not called light when the frequencies are quite low. When the frequencies then start to go very high, if you look towards the right-hand side of the spectrum, you then start to move into things like ultraviolet. You then start to move into things like X-rays, etc. Now, a lot of you will speak a little about the relationship as well of the frequency to the actual wavelength. So a wavelength of a particular wave is essentially what is the length of the wave, right? So you'll find that over a particular time period where a complete cycle of the wave is allowed to complete, that tells you the actual wavelength. So in some instances, you'll find towards the left-hand side of this diagram, you have a low frequency, but the wavelength tends to be longer. As you move to the right-hand side, the frequency starts to increase, which therefore means that the wavelength gets shorter, right? So the sort of zero-sum type of relationship or inverse relationship that you're seeing between the two goes down to the fact that everything is limited by the speed of light. If anybody knows, just by the way, offhand, what is the speed of light? It'll be great if you can actually pop that answer into the chat. You don't need to be supremely accurate in terms of the number itself, but if you've got an idea of what that looks like, go ahead and pop that into the chat. Right. So concentrating more to the bottom end of the spectrum or the diagram, you'll start to find that there's a radio spectrum. Now, within the radio spectrum itself, tons and tons of use cases exist. Okay, so we have things whereas a lot of you are listening to radio, right? So radio, we know that to be things like medium frequency, you have high frequency, and you have VHF, which is your very high frequency. You have mobile telephone networks that basically operate on the UHF sort of band, which is ultra high frequency, which is kind of around about the gigahertz type range. You have satellites that are more on the microwave sort of spectrum, which is the an extremely high frequency range. But also remember on the low frequency side, you've also got various other applications like communications networks, etc. The other aspect here, so once we move out of the radio spectrum, just a very quick note, you'll start to find the scale above where we talk about frequency. You'll see it says 1 kHz, 1 MHz. So you'll find firstly, frequency is measured in a unit called hertz. Hertz is basically number of cycles per second. The K in front, so kHz, basically talks to we learn this from a scientific perspective and measurements perspective, where you have multiples and submultiples. So a kilohertz is basically 1,000 hertz. A megahertz is essentially 1,000,000 hertz or 1,000 kilohertz. A gigahertz is essentially 1,000 mega, or that'll be 1,000,000. So consider it to be 1 billion. And then it goes on in terms of tera, peta, exa, right? So it can go to very large numbers. There's also a micro world that exists. So you also have submultiples where you divide by 1,000. Again, for homework, you could just go and do some research on milli, micro, nano, pico, just by way of example. So you're welcome to share your thoughts on the micro world on the Canva platform. So we've covered elements of the radio spectrum itself. As we now move into higher frequencies, so remember, microwaves are used to warm food. A lot of you would probably have a microwave in your kitchen, and it's just added a level of convenience, to the modern world, like no other. Moving now into the light sort of spectrum. So you'll find, I want to tell you a very, very quick story in terms of an experiment that was carried out some time ago, where we had a scientist that was playing around with light and trying to understand what made up the different elements of light. So what he did was he passed light through a prism, right? And he noticed that the light then obviously split into the different color bands, right? A lot of us basically would call that a rainbow, right? And we'll cover aspects of the specific colors. But purely by accident, right? And fortunately, on the right side of that color spectrum, this particular scientist had a thermometer just laying around because I mean it's very easy to find a thermometer in a typical lab. And just, what he then noticed was when the light was then split, he noticed that the thermometer reading started to go up. And he found this interesting. He did a couple of tests and he moved the thermometer around. He took it out of that particular position. He placed it in the middle of the color band, and he noticed that there was no impact. But he noticed that when it was specifically to the left of red, the thermometer reading started going up. And what he discovered then was infrared, right? So essentially, infrared is not something that we can see, but it's something that we can actually feel, right? So a lot of you have built-in sensors on your skin where your body can actually detect a change in temperature. So a lot of people typically make use of infrared specifically for warming. So that warming effects that you feel out in the sun as well are basically the infrared rays that are coming through that you can't really see, but you can actually feel it. There are also specific types of lamps, right? During winter, you have these infrared lamps that also warm you up. If you ever wondered why, when you light a fire, just by way of example, remember that there is infrared coming out from the fire, and the warmth that you feel is essentially an infrared ray that's coming towards you. So, and a way to test this, and actually to annoy somebody, you go and stand in front of them. When they're sitting in front of the fire and you stand in front of them, they will complain that they do not feel warmth anymore. And that's because you are now absorbing the infrared and they're not getting the benefit of the infrared. So that's the reason why, you would never stand in front of somebody, I guess, around a campfire. Um, so you've got infrared. We then have the visible spectrum, which we all affectionately know as Roy G. Biv, and the different colors of the light spectrum. Something in here that a lot of you may not have realized, but every single type of color of light has a specific frequency. Okay, so depending on the frequency that's basically coming through, that determines the color of the light that you're able to see. And remember that your eye is a very special type of detector in terms of picking up the spectrum of light. Now, as we move away from violet, which is the last visible sort of element that we can see, just by the way, if we look at Roy G. Biv, a lot of you might wonder, why is it that we have indigo and violet, two colors that are fairly close to each other. And apparently the story behind it is that the particular scientist that came up with it loves the number 7, and also specifically loves the color indigo at the time. So it really was just inserted as convenience, and because he likes the number 7. So fun little fact there. Moving finally at the last right-hand side of the electromagnetic spectrum, we then move on to things like X-rays and gamma rays. Now, a lot of you know X-rays have the ability to show you what your skeleton looks like, right? Very key factor that you can now start to see is that as you move to the higher end or the higher frequency end, you start to find waves that can start to penetrate, right? Whereas the lower frequencies have less of an ability to penetrate through something. So if you take a typical radio wave, a lower frequency radio wave would have the ability to go through, will be absorbed by things like buildings, etc. Whereas the higher frequencies would have the ability to penetrate through the buildings. Think about your mobile cellular telephones. They do use a very high frequency because that allows it to penetrate through buildings, etc. So of course, at the X-ray side, it does have the ability to then penetrate through your skin to then expose exactly what your skeletal makeup looks like. So lots more really to cover around the slide, but just for the purposes of the questions that you've got coming up, this is more than adequate. But again, lots of elements here for you to go and do some self-research on. So yeah, I guess just really to summarize, there's quite a few different relationships here. We know that where you have increasing frequency, you have decreasing wavelength. So higher frequencies, you have shorter sort of wavelengths. Yeah, if you pick up the answer to my question earlier on in terms of what is the speed of light, it's around 300,000 kilometers per second, which is quite fast. So just some very quick points. The more frequency, the more energy a wave actually has. Oh yes, of course, the very key aspect around waves, electromagnetic waves, they do not require some sort of medium. Excuse me, if you now compare this to the mechanical waves that we spoke about, remember sound waves is essentially a mechanical wave, which does require a medium. So if you think about space, right? Why is it that you cannot hear somebody talking? Okay. But why is it that we can transmit audio or video from, say, a satellite station down to Earth? If you know the answer, again, pop it into the text box or onto Canva itself. Okay. The other thing, as we spoke about as well, is that there's an inverse relationship between the wave size and frequency. So key elements just for you to understand this world around you. Infrared waves, and we said it's basically heat. Invisible light, we've spoken about that. Okay. Yeah, and of course, just to bear in mind that the visible light is a small part of the electromagnetic spectrum, meaning that the most part of the entire spectrum we can't really see, and we need other types of detectors or sensors to be able to pick them up. Okay. Yeah, so we spoke about Roy G. Biv being the different colors that you have coming out from white light. Very quickly about lasers, I think it's a very, very interesting concept. Very cool thing to go and write a little research report on. But essentially, the basic mechanism of a laser is that you have a sort of piece of you're typically made up of a glass type of tube, and there are different types of medium now available. And what actually happens on the one side is that you shoot a stream of light, and you then have this light then reflecting. It bounces off the one side of the inside of the tube, and it bounces off the top again. The phenomenon there is something called total internal reflection. So it basically bounces around internally from one end to the other until a sensor at the other end is able to detect the light coming through. Okay. So you'll find that a lot of modern day communications, in fact, guaranteed that we are speaking to each other definitely over a fiber optic cable. And of course, fiber optics make use of lasers internally, etc., to communicate from one to the other. And that's what the most part of the internet really is made up of, right? So for long distances, connectivity happening under the ocean, for connectivity happening across continents, for example, we make use of fiber. But of course, where we can't run fiber, we then lean onto the electromagnetic spectrum for things like radios and satellites to then connect us into areas that don't really take us, that we basically are unable to run fiber to. There's a whole bunch of other little points that I've placed here, but I'm just quickly going to skip through those. Just bear in mind that this presentation will be made available to you on the Canva platform. Okay. Yeah, just interestingly, one of the pictures, remember that in this particular instance, we can see is something called a scintigram. But yeah, it makes things kind of look visible. Again, these are things that we potentially can't just see with the naked eye, but we use a different range of techniques and science to basically reveal what's going on. So, for example, if there's a doctor on the call, you know, this is exactly what an asthmatic a person's lungs would look like. So lots of applications for the different types of waves out there. Um, yeah, so very, very quickly, these items that you see up here, firstly on the left-hand side are radio antennas that are made used to transmit up to satellites in the sky. You've got a little very old radio that's kind of in the middle there. And then, of course, it's a very quick picture of microwaves. So common factor amongst all of them is that they're all making use of waves in some sort of way. Various different applications so of course there is a use case for every single type of frequency. The interesting thing about this range of frequencies, every country, just like every country has, a lake or a river or a dam as its natural resource, or you have an ocean as part of your natural resource, or you've got a forest as your natural resource. Radio waves are now considered to be natural resources. And the reason for that is that there is a finite supply of radio waves in your country. So you'll find that a lot of these different frequencies are typically managed and regulated by your local regulator, right? So it's very important to have regulation. Why do we need regulation? Well, one of the things that radio waves suffer from is basically interference, right? So wouldn't it be horrible if you made a phone call to somebody and you then find another person talking over you, right? So firstly, your conversation won't be private. If you're listening to your favorite radio station, wouldn't it be terrible if your neighbor was sort of transmitting something else that wasn't interesting to you, right? So because it is naturally occurring, remember that it is definitely impacted by interference, and therefore we need regulation for this. So in South Africa, just by way of example, an organization like ICASA would manage the regulation of the various different frequencies. Yeah, and of course, multiple different applications. So you could have radio astronomy, which makes use of EHF waves. Space and satellite would make use of SHF waves. Your television and some radio would make use of VHF and UHF. Shortwave radio and AM radio would make use of your medium frequency and your high frequency. And of course, if you're out on the ocean, you actually rely on VLF or very low frequency waves to help you with navigation signals. So lots and lots of applications for all of these waves. So, there is a use case for the science behind all of this. So we know about waves. We know that we can transmit it in a certain way, but how do we make it useful to us? The one way is to actually transmit information, right? So we spoke about fiber optics and how you could pass light over very long distances. We spoke about radio waves. You can transmit information from one end to the other end. But the way we do that is through modulation, right? So if you think about your radio, when you listen to the radio, some of you are familiar with AM and some of you are familiar with FM, right? So AM stands for amplitude modulation. and FM stands for frequency modulation. Now, there are pros and cons to using, both types of these. Um, but essentially, the way it works is that you have a standard carrier signal that is basically typically centered around the frequency that you have licensed, right? So if you are an FM transmitter, you would have been assigned a particular sort of frequency. So, for example, I think a local radio station that I listen to is something called KFM, and KFM transmits on the specific frequency of 104.7, right? So you'll find a lot of these radio stations make use of these numbers, and these numbers typically talk to the licensed frequency that they are only allowed to transmit on. So that carrier wave is basically centered around the frequency that they have been given. What you then do is you then provide the information to be modulated into the carrier. So when you then provide a modulation onto the carrier, so you could take the information and you can play around with the amplitude, right? Vary the amplitude in line with the actual modulation or information that you're receiving. So here again, an example of the modulation you might receive would be my audio. As I'm talking to you, it modulates the amplitude accordingly. And when the radio wave is transmitted to the other side, you're able to extract, right? You're able to then separate out the carrier and the actual information from the actual signal, and then listen to the audio coming through. Another way to do that is by not modulating the amplitude. So amplitude here, as you can see with the green wave, is essentially the size of the wave, okay? If we modulate the frequency of the wave, remember to see the difference of frequency modulation, you'll find some waves are compressed. Where it's compressed, it's a high frequency, and where it is stretched out, it's a low frequency. So you basically modulate the frequency of that particular wave according to the information it's receiving. So again, in this example, it would be me talking into the microphone, right? So it starts to modulate that. Some of the basic pros and cons of the two, you'd find that amplitude modulation has the ability to travel further, right? So you can actually pick up an AM signal much further away than you can with an FM type of signal. So you'd find, FM is stronger within metropolitan cities, right? You'll pick up your favorite radio station within a city, but as you start to drive away from the city, it becomes more and more difficult to actually connect to it. Whereas you might have a greater chance of listening to an AM type station. Another key visible, clear difference between the two as well is the quality of the audio that you're getting. So typically on an FM radio, it's almost high definition audio that you're able to get. You're also listening to it in stereo, whereas amplitude modulation, you don't get a lot of clarity. You could just pick, and typically you find things like talk radio stations would transmit through an AM type station. So even though we say that, video killed the radio star, rather than now modulating radio signals, audio, there's also video that can also be transmitted through these types of signals. But yeah, it'd be great to sort of get your comment on, did video really kill the radio star? Does radio still exist? Is there still a place for radio today? I'd love to hear your comments and feedback on that. Just doing a quick time check. Gosh, yeah, we're running out of time already. Just very
it's
quickly.
going well, Colin. Yeah, it's going very well. There's been quite a bit of chat.
Oh, great.
On the side here. Yeah, absolutely. A number of different propositions in terms of the speed of light.
Great.
3 million meters per second from Josh. And then we've got 186,000 miles per second from Seth. And that was then translated into meters per second, very close to Josh's number, 299 million, etc. And yeah, and then we've also just been, I was putting in some notes for everybody in terms of kilo, mega, and giga. Micro,
Great.
nano, pico is that kilo is 10 to the power of 3, exponential 3, mega, exponential 6, giga. Sorry, that was meant to say, 9. And then a nano, micro, nano, pico, then we look at -3, -6, -9, etc.
Correct.
So
Correct.
yeah, I'm
Excellent.
very the learning those was very important for me when I did physics and chemistry,
Mhm.
so that I could really understand the difference between a microgram and a kilogram,
Yes.
etc. And so that one actually knows what one starts getting a feel for all of that kind of thing. And then, Josh, do you want to unmute and share with everybody your observation about microwaves?
For the microwaves, what I said was that the holes on the screen of a microwave is actually small enough so that the microwave radiation can't pass through, but it does allow for the visible light to pass through. So when you look in to see your food, your eyes won't actually get heated up, but you can still see your food inside.
Absolutely. So yeah, that was
Interesting.
really great. Thanks. A very practical application. And yeah, so yeah, there've been a number of different submissions, Zeal as well, in terms of
Excellent.
speed of light. Zeal, you wanting Josh to repeat that? Please just have a look in the chat. He just describes that for us. Collin, yeah, let's go back to you. If it's okay,
Great.
we have, let's say, 10 to 15 minutes, if that is okay.
That's just about perfect. Thank you very much for that, Judy. And yeah, great. I can't really see any activity from a chat perspective, so it was good to get that feedback and know that you're all having a. Like I said, yeah, let's have a conversation. Go ahead and pop through some of your most interesting concepts that perhaps not many of us actually know about. But I like the little example, Josh, in terms of the microwave. So any interesting stuff that anybody else could share, go ahead and pop that in. Yeah, and another thing to sort of think about as well is a lot of you are familiar with the atmosphere and the stratosphere, etc. And there's also a really good friend of ours, particularly if you are a ham radio enthusiast. It is the ionosphere, right? And what we typically make use of this is, firstly, a lot of communications happen from a line of sight perspective, right? Line of sight meaning, can you actually look, can you see from one point to the other? Now, if you are a flat Earth subscriber, this is a point you probably cover your ears and block your eyes. But yeah, the Earth is actually round, okay? And because of its curved nature, line of sight can only work up to a certain point, right? So at a certain point, you are not able to see from one point to the other. So if you think about a radio wave and you are transmitting from the one side and it relies on line of sight communications, we actually can make use of the ionosphere to bounce off the signal. So you basically shoot the signal at a particular angle. It bounces off the ionosphere. It can then bounce off the Earth, go back, and then hit the receiver on the other end. So you would then have the ability to communicate, even though you can't really physically see the other side of your transmitter. And that's how we can actually get radio waves to propagate even further, right? So very, very interesting use case for the ionosphere specifically. Now this bit is, I think if we cover at least this, you would be ready to answer a lot of your questions. So a lot of the questions at the end are based on these equations. Okay, so you're welcome to refer back again to these particular elements. But some of the characteristics of a sound wave, for example, we spoke about amplitude. So amplitude is basically the displacement from the zero sort of axis to its highest point. Some of you might think of it as a volume, right? So if you're listening to some audio, or if you're listening to the television, the volume that you're hearing is really can be translated to the amplitude of the particular wave. When you look at the wavelength of a particular wave, you'll find that a wavelength is represented by the Greek letter lambda. And wavelength is really the distance between two peaks or two troughs. Okay, so that's how you could ultimately measure what your wavelength would look like. Then, of course, some of the if you look at another graph around a high frequency wave versus a low frequency wave, if you push the waves to closer together, it means that more waves are basically being transmitted during that period. Therefore, it's considered to be a high frequency wave. Compared to a low frequency wave, you'll find that, think of the slinky being stretched out. You've got, fewer sort of elements of the wave being transmitted within that particular period. So just visually, what a high frequency versus low frequency ultimately looks like. We spoke about the volume being related to amplitude. So when you have something that is quieter, it's a wave that essentially has a lower amplitude. When you have something that you hear that is louder, it essentially has a higher amplitude. Another concept to think about is when you look at frequency, anything that has a low frequency is considered to have a low pitch, right? So if you think about a bass drum, okay, typically a bass drum has a low frequency and therefore considered to have a low pitch. When you, for example, blast through a trumpet, if you actually visualize the sound coming from a trumpet, you'll start to see that it has a high frequency. So here again, you've got a higher pitch. But again, you could give us examples, if you like, of low amplitude and high amplitude, and low pitch versus high pitch. So very happy if you could share some examples there. In terms of the mathematics that I promised you, so essentially we have the first one, which is V equals your lambda times frequency. Remember, lambda is your wavelength. In this particular instance, V is velocity, or the speed of the wave, right? Now we know that with if it's with electromagnetic waves, there is a very, very specific speed that the wave travels at. And some of you have had a discussion on that already. And typically, the speed of light has a very specific letter, and it's typically represented by the letter C. All right, so wherever you come across C, we are talking about velocity, but specifically the speed of light. T, or the period of a wave, is equal to 1 over frequency. If you rearrange that around a bit, you'll find that frequency is also equal to 1 over the period, right? So the period, or T, is also, you sort of calculate it if you take the time that a wave gets from one point to the other and the number of cycles that happens, that'll give you your T. If you're looking for the F, or the frequency of a particular wave, you then take the number of cycles, you divide it by time, and it gives you the cycles per second. Remember, cycles per second from a unit standpoint would be in hertz. Okay. But yeah, you'll have access to that particular slide as well as part of the deck that will be uploaded. Now, as I mentioned earlier on, we spoke about the internet, and there are various different connectivity options available to use. We have wired, we have wireless options. Wired, remember, you typically find within metro type areas. This could be copper wiring, it could be Ethernet wiring, it could be fiber optics. But as we move more into rural areas, we then sort of switch over to wireless, because the cost element, sort of changes quite drastically. Remember, wireless also takes into account things like satellite connectivity. Okay. So the internet is essentially a whole big interconnection of multiple types of networks that are connecting information. Remember, a website that might be sitting in Australia is being accessed by somebody in Rwanda through, maybe it's a wireless connection from your home in Rwanda to your local internet service provider. The service provider then connects through to a cable landing station through, say, a copper cable. The cable landing station then connects, through an undersea cable, which basically runs through fiber optics. That then gets to the other point in Australia, say at the cable landing station. The signal might then be carried from the landing station through to an internet service provider in Sydney over microwave, right? A point-to-point microwave link. And then ultimately you've got the server sitting at a data center, which then connects over copper cables. So that entire pathway, you can see, can be made up of multiple different types of connectivity elements. And we've actually discussed quite a bit of the science and physics behind how these different communication elements work. The internet is really a complex network system. It's made up of multiple different routers and switches. So those are the two common devices that basically connect all these different types together. And I think that's really what I'd like to convey from this picture. Again, various different use cases. You start to find that the closer you are to a metro area, you start to make use of things like fiber, coax, and copper. And then, of course, as you move more to the rural side, you are sort of mostly dependent on wireless type connectivity. So which is why you'll find different types of connectivity when you're in the city versus to when you're probably on a farm somewhere. Judy sort of opened out talking about IoT. IoT is basically the Internet of Things. And you'll start to find that there's a range of different technologies that can be used to connect up various types of sensors. So things like moisture sensors, things like temperature sensors, etc. And we can come up with a range of different technologies to connect them up. And you'll start to find that this sort of aligns itself quite nicely to the UN SDG 7 when we start to consider affordable and clean energy, right? Remember that if you look at power consumption for the different technologies at the bottom, there are, of course, different pros and cons. In some instances, a lot of these connectivity options use a lot of power, where a lot of them make use of low power elements. What this simply means is that you could run a sensor on a battery for much longer if it's highly optimized from a power perspective. Whereas if you look at something like connecting over 5G, and we've got a little temperature sensor out in the river somewhere, it can't run on batteries for too long because of its power consumption. It starts to consume a lot of battery power, right? So again, you need to really be really familiar with the different types of connectivity options, what their ranges look like, and there's always a trade-off, right? You have range versus power consumption versus the speed of the actual data itself. So very quickly, from a satellite perspective, satellites essentially use line of sight, connectivity in a sort of way. So for example, you've got the transmitting antenna in one continent, and you've got a receiving antenna in another continent. Now, they can't see each other in this particular instance, and they also can't make use of the ionosphere as well, depending on the frequencies that they need to transmit. So what they then do is that they point their antennas up to a geostationary satellite. So basically, it's a satellite that stays in sync with the rotation of the Earth. And what it simply means is that, therefore, the one transmitting antenna will always have that particular satellite point in sight. So think of the satellite as a mirror. It shoots up the signal to the satellite, and the satellite then pushes down the signal to the other side. And in some instances, it's also bidirectional, right? It also allows for connectivity in the other direction. That's essentially how satellites communicate. A quick word on Starlink. A lot of you would have come across this really cool concept by Elon Musk and SpaceX, where they've decided to shoot thousands of satellites into space that orbit the Earth constantly. And essentially, it is a mesh of these satellites that allow us to start to then communicate. Couple of points in terms of Starlink. One is that it is now considered to be a replacement for fiber connectivity. So if you think about people in the rural type areas, if they're making use of Starlink, it could give them very similar connectivity experience as you would with fiber optics in the metro. So therefore, Starlink is becoming, something really big and really something that a lot of people are considering making use of. However, the key element behind Starlink is that it is designed essentially to be deployed on Mars. So if they now shoot satellites that start to orbit Mars, we would then have the basis for interplanetary communications, right? So somebody that's located on Mars would be able to communicate to their mesh of satellites there. There will be a backhaul link that goes from Mars to Earth, and then, of course, reach the mesh around Earth itself, and immediately you now have interplanetary communication. So it's a day that I am absolutely waiting on. In terms of your kit, some of the questions that we sort of looked at is there are quite a few different radio frequency transmitters on your kit. I'd love to hear what you think these are, if you could list them out. And also if you could do little experiments to sort of look at what is the impact on power, right? And it'll be great to hear how you come up with experiments to test this, right? Tell us if you leave a particular device on, how long will it stay on battery power? If you turn it off, how long will your kit ultimately stay on battery power? So neat little experiments that you could go ahead and design on your own. What are the different connectivity considerations that you would have on Mars? Think about how do you communicate from one little habitat to the other on Mars? Could you potentially communicate from your habitat to family back on Earth? Think about the different sensors that you might have deployed across the planet itself, and how would those sensors communicate with itself? Zeal, yes, you've got your hand raised.
Yeah, that's the question in the chat, but I'm not sure you can see it split. Okay, yeah. So what I was asking in the chat was that since radio waves or like EM waves move at the speed of light, and the distance between Earth and Mars is pretty substantial, does it mean like even with the satellite communication, a hello from me, like me saying hello from Earth could be received about 3 minutes later from Mars. Like the communication with the communication moving at this.
Zeal, sorry, I got your question, but it came across, it was quite broken up. I think it sounds like you might be on Mars yourself, but but I think I picked up. I got your question right. So it is. I think it's got to do with the of course there's a distance between Mars and Earth itself. You're probably asking about the delay and how long would it take for communications to happen across. So yes, of course there's going to be delays. There's a lot of orbiters as well that we currently make use of. We've got multiple different telescopes that are flying into in space, and for them to communicate back to Earth, they then use repeater stations, which are basically orbiters. They bounce the signals off those to ultimately transmit back. There are some technologies I know that SpaceX are looking at, and feel free to research and share some of your ideas again on Canva itself, where they're looking at high-powered laser beams, to go from the mesh of Starlink around Mars to the mesh around Earth to sort of get a direct sort of link of a laser. But ultimately, there will be some type of a delay. If you think about current communication through satellite, it's always been a concern. A typical satellite today gives you around about a 650 millisecond delay. Using something like Starlink, because it's a low Earth orbit type satellite, I think you're able to even get something to around about 10 milliseconds is what they've been able to achieve. But yeah, we've learned how to deal with delay. Remember that in a call or a conversation, if I'm broadcasting a picture or audio, it will be a constant stream, right? Because you've buffered all of the information and everything's been transmitted at the same time. It's just that initially there will be a delay before you start getting the stream coming through. But yeah, I mean, we can have a very nice conversation on delay, particularly around interplanetary communications. Also do some research on things like, radio telescopes in space, on satellites as well, and how they communicate back to Earth, and look at, try to do some calculations, right? Look at the distance between the two planets, the speed of light. You can very quickly sort of come up with a calculation in terms of what would the typical delay be from this calculations. But yeah, cool questions. You'll really appreciate that. But yeah, please, we'd like to have a conversation with you on Canva. More questions and comments on that. In terms of your assignment, some interesting points to cover is, can you do a quick distance check on your kit? How far away? Remember, your kit currently talks to the internet over your local access point or Wi-Fi. And the further away that you move from your access point, your signal starts to degrade. I mean, you all know this, right? From a Wi-Fi perspective, you got to run quite close to the house. Once you move outside of the house, your signal completely goes away. So I'd like for you to do an experiment to sort of test, the distance from your Wi-Fi. Also test what types of signals interfere with your Wi-Fi signal, right? So if you go to a different room, you now have a wall in between you. If you've placed a big piece of metal, what is the impact on that? If you place a big piece of wood, what is the impact on the signal? So just do a whole bunch of little tests like that. And then also, if you can also share with me, what is the furthest distance away from your Wi-Fi access point that any of you can get before you lose signal? So we could think of it as kind of a competition, right? Let's see, and you need to have some sort of evidence to show us that you're able to communicate from a certain amount of distance. So think about how you are going to carry out the experiment, and think about how are you going to capture the evidence. Many different ways of doing this. One of the tips that you could consider using would be on your on the actual dashboard itself. A lot of you would be using the Kibana dashboard. There's a lot of interesting statistics, right, in terms of the signal strength. There's a particular metric which talks to RSSI. So if you look at your dashboard, look at all the data that's been logged on your specific device, and there's something called RSSI. So do some research on that. That basically gives you the signal strength of your Wi-Fi. So you can make use of that. But yeah, that's for your assignment. That needs to be completed during the next couple of weeks. And then, of course, there's a whole bunch of questions here. So a lot of these questions you'll see are based on very basic calculations. I mean, I think the majority of you should be able to complete this work in an hour. Don't worry about screenshotting this or whatever. Like I said, the entire presentation is shared on the platform itself. Yeah, and I think that is it, people. I think, yeah, I've seen we've got quite a number of people that were on. I've seen the number of participants shoot up to around about 23, and I see it starting to fall back just yet. But for those of you that have stayed on, thank you for taking the time and sticking around for the long haul. Really interesting conversations and questions popping up. Yeah, let's keep the conversation going. Hop onto Canva, share some of your thoughts and questions there. But yeah, I guess for now, thank you all for joining me this evening. And I guess we'll chat to you online. But yeah, folks, thanks very much. Have a great evening. Be safe and chat to you soon. Take care.